Students, today I will discuss types of errors. There are two types of errors, type 1 error and type 2 errors. Type 1 error, the error of rejecting H0 when H0 is true is called type 1 error. The probability of type 1 error is known as its a size and it is denoted by alpha. That is, alpha is equal to probability of type 1 error. It is mathematically explained. Alpha is equal to probability of rejecting H0 when H0 is true, or equal to probability of X belongs to C under H0 where C is critical region. Similarly, type 2 error, the error of accepting H0 when H0 is false is called type 2 error. The probability of type 2 error is called as its size and it is denoted by beta. That is, beta is equal to probability of type 2 error or equal to probability of accepting H0 when H0 is false. That equal to probability of X belongs to C under H1. Here H1 is alternative hypothesis. Next, power of the test. The power of the test is denoted by 1 minus beta. Already you know beta. Beta is probability of type 2 error. Next, critical region. Simply CR. The region of rejection of H0 is called as critical region or CR and it is denoted by C. The region of rejection of H0 is true is that is region of the outcome set H0 is rejected if the sample point falls in that region is called critical region. Critical region explained below diagram with example. Draw the normal curve. Center line is called Z is equal to 0. That area is called acceptance region. Right side, that mark dot mark, rejection region. Left side, dot mark, rejection region. Level of significance, it is denoted by alpha. The probability of type 1 error is known as the level of significance of the test. It is also called as size of the critical region and it is denoted by alpha and is given by alpha is equal to probability of type 1 error that equal to probability of rejecting H0 when H0 is true. Note, level of significance is always fixed. Next, sampling distribution of X bar and S square. Derivation of joint distribution of X bar and S square. Let x1, x2, so on xn be a independent random variables. Xi follows normal with mean mu I variance sigma I square. I is equal to 1 to n. If xi's are mutually independent, then summation Ci xi I is equal to 1 to n follows normal with mean summation ci mu I is equal to 1 to n, variance summation ci square sigma square I is equal to 1 to n. Therefore, mgf of summation ci xi I is equal to 1 to n is given by mxt. It is notation of moment generating function, that equal to expectation of e raised to t into summation ci xi I is equal to 1 to n equal to expectation of e raised to t into ci c1 x1 expansion e in expectation of e raised to t into c2 x2 so on. Last term expectation of e raised to t into cn xn. Here xi's are independent if x follows normal with mean mu variance sigma square. Then we have expectation of e raised to tx is equal to e raised to mu t plus half into sigma square t square. Already you know in first semester mgf. Therefore expectation of e raised to t into ci xi, that equal to e raised to mu I ti ci plus half into ci square sigma square t square. Therefore moment generated function, that is mxt, is equal to summation e raised to ci mu I t plus half into ci square sigma square t square, that equal to take summation inside e raised to summation ci mu I t plus summation ci square sigma square t square divided by 2 I is equal to 1 to n. This implies summation I is equal to 1 to n ci xi follows normal with mean summation ci mu I variance summation ci square sigma square. Now expectation of x bar is equal to expectation of 1 by n summation xi, since x bar is equal to 1 upon n summation xi, that equal to 1 upon n summation, say, take expectation inside expectation of xi, that equal to 1 upon n summation mu, since mu is equal to summation expectation of xi, that equal to n into mu divided by n, since mu is constant, that is why n mu, n cancelled, that equal to mu, since variance of a is equal to 0, means constant terms, always variance of constant terms becomes 0. Now putting mu1 is equal to mu2 is equal to so on equal to mu1, that is equal to mu. Similarly sigma 1 square is equal to sigma 2 square is equal to so on is equal to sigma n square, that is equal to sigma square. C1 is equal to C2 is equal to so on is equal to Cn, that is equal to 1 by n. Now it follows that y is equal to x bar into n into s. A normal distribution with expectation of x bar is equal to 1 upon n summation mu, already explained about term, that equal to n mu divided by mu, n mu divided by n, that is equal to mu. Therefore expectation of x bar is equal to mu. Similarly find out variance. Variance of x bar is equal to summation 1 upon n bracket square into sigma square I is equal to 1 to n, that equal to take 1 upon n square, that is summation I is equal to 1 to n sigma square, that equal to n into sigma square root by sigma square. Here sigma square is constant, that is why n sigma square root by n sigma square root by n square, that is equal to sigma square root by n. Therefore variance of x bar is equal to sigma square divided by n. Expectation of x bar is equal to mu and variance of x bar is equal to sigma square by n. Thus, sample distribution of x bar from a normal population, it follows, that is, symbolically, x bar follows normal with mean mu variance sigma square by n, where x bar is equal to 1 by n summation I is equal to 1 to n. Now, to obtain the distribution of S square means variance of sample, we shall first show that the independence of x bar with, that is, x1 minus x bar, x2 minus x bar, so on xn minus x bar. This will become ultimately show that the independence of x bar and s square, that is s square is equal to 1 upon n summation xi minus x bar whole square I is equal to 1 to n. This implies ns square is equal to summation xi minus x bar whole square I is equal to 1 to n. Now, the technique of MGF means moment generating function. We have mx of t1, t2, so on tk, that is equal to expectation of e raised to t into x plus t1 into x1 minus x bar plus t2 into bracket x2 minus x bar plus and so on plus tk into bracket x minus xn minus x bar. We know that previous formula mxt is equal to expectation of e raised to tx. Now, first term expectation of e raised to x is nothing but integration of minus into infinity plus and so on integration of minus infinity to infinity 1 by sigma into square root of 2 phi bracket raised to n into e raised to t into x bar plus t1 into x1 minus x bar plus t2 into bracket x2 minus x bar plus and so on plus tk into bracket xn minus x bar dx1 dx2 so on dxn means with respect to x1 x2 so xn, that is equation number. The integration can be factorized as exponential function of xi's for particular xi. The factor is given below, that equal to e raised to t xi divided by n plus ti xi so on t1 plus t2 plus so on plus tk into bracket xi divided by k minus xi minus mu whole square root by 2 sigma square, that equal to e raised to n into 1 by k into t plus k into bracket ti minus t bar xi divided by k minus xi minus mu whole square by n upon sigma square 2 sigma square. Here the component of mx of t1 t2 tk with respect to a particular xi is given by, that equal to 1 by sigma into square root of 2 phi integration of minus infinity to infinity e raised to xi divided by k into bracket t1 plus k into bracket ti minus t bar minus xi minus mu upon 2 sigma square dxi, that equal to expectation into bracket e raised to x divided by k into bracket t plus k into bracket ti minus t bar, that equal to mx into bracket t plus k into bracket ti minus t bar divided by k. Since expectation of e raised to tx is equal to e raised to mu t plus half into sigma square t square, this is the formula. Hence, the k dimensional integration of I on the LHS of equation 1, which represents m of t1, t2, so on tk, being the product of I1, I2, so on ik, where ii is represents the construction with respect to xi. Now we have I is equal to I1, I2, so on ik, that equal to e raised to summation into bracket mu upon k t plus k into bracket ti minus t bar complete bracket plus sigma squared upon 2k square into bracket t plus k into bracket ti minus t bar whole square, that equal to mx of t1, t2, t2, so on tk. Now x bar and s square are statistically independently distributed. Large sample test, normal test. Large sample test for single mean. Let x1, x2, so on xn be a random sample from normal population with mean mu and variance sigma square. Then the distribution of sample mean x bar is given by x bar follows normal with mean mu variance sigma square by n. Even if the random sampling is normal, then the distribution of x bar will be normal for large n. Thus, the population statistic is given by z is equal to x bar minus mu, this divided by sigma by root n, follows normal with 0, 1. It means standard normal variate. Next, for large values of capital N, the hypothesis to be tested with there is no significant difference between sample mean x bar and population mean mu. That is, h naught such that x bar is equal to mu naught. And the alternative hypothesis h1, that is h1 is equal to x bar, that is equal to mu 1. Therefore, the critical region will be located both the tails of the normal distribution below normal curve. The curve, the left side alpha by 2, that is minus z alpha by 2, right side alpha by 2 plus z alpha by 2. If x bar minus mu upon sigma by root n lies outside the limits minus z alpha by 2 and z alpha by 2, explain previous normal curve, then h naught is rejected or expected. h1 such that x bar greater than mu naught, h1 such that x bar less than mu naught. The critical region of size alpha will be located only on right or left tails respectively. If the variance sigma square is unknown, then we estimate s square, that is s square is equal to sigma square for large sample. Thank you.